Hi, hey everybody. Welcome back to the world of calculus, where I'm now going to go over the second lesson of limits. So let's get going. We're going to look at how we find limits and study them by using graphs, analyzing and studying, checking out graphs, and by using a numerical approach, meaning that we're just going to be kind of looking at numbers, plugging them in, kind of being tedious. But let's just get straight to some examples because that's always the best way to learn. So let's start off with this function, f of x is equal to x cubed minus 1 over x minus 1. And again, right now, don't worry too much about the graph. At this point, graphs are probably going to be given to you, and it's not a game. It's not. We're not trying to test and practice our graphing skills. So we just have this graph. Let me see if I can. I'll just put it over here. What the heck? Is that crooked? I have to stick with it. Gotta practice. So we have this graph, and it looks somewhat like a parabola, but it's not. This is going to be that shape. And I don't know I have this marker in my hand. I want this one. Okay, so so for this graph, we have essentially an undefined value at x equals 1. So at the point 1, comma 1. 1 comma, sorry, my camera just blanked. 1 comma 3. I'm new at this, as you can tell. Not new at math, but new at this camera recording thing. Anyways, so this graph is going to have what we call a hole at the point 1 comma 3. It's a point of discontinuity. It's undefined, if you want to look at it that way, many different ways, but we call it a hole. That's really the name that we use in math. When you have a point of discontinuity, where the graph essentially skips it, so to speak. Now, when we're talking about limits, let's say we want to understand what's going on as the graph approaches positive 1. We can approach it from this side, or the left side, or the negative side, we say, or from this side, the positive side. And so what we write is the limit, abbreviated just LIM, the limit of f of x as x approaches 1. So underneath the limit, or the LIM, we put x with an arrow towards 1. We put this is equal to, in this case, 3. This is an example of a limit being defined where there is actually a hole on the graph, or it's actually, the function is undefined. So it's like saying, it's, in other words, if we have f of 1 does not exist. That doesn't mean that the limit can't exist. So that's the first concept I want to get across here. So at first when you see this notation, it can be a little weird, but don't worry, it won't be weird pretty soon, or hopefully pretty soon. So let's just keep on doing examples because that's how we master this math world. I don't know why I drew that line. Let me erase it. Next example, let's look at the function x over the square root of x minus 1, or the square root of x plus 1 underneath the radical, and the minus 1 outside of it. So this guy. And again, don't worry about how we get the graph. In this section, like in your textbook, you're going to be given the graph usually, or just use your graphing calculator. So this graph will look like this, somewhat of like a square root behavior. Let me just use red actually. So veering off like this, starting from -1, 1. And we have a hole at 0, 2. Another hole. Ooh. Yes, I am a little immature, but anyways, let's just make sure we understand this concept of a hole and in limits and in calculus. It's just a point of discontinuity where you kind of jump over. The only x value we skip along this region is 0. And it's still undefined at 0, so f of 0 does not exist, we can say. This is true, but the limit exists, because as we approach 0 from either side, from the right or from the left, we have the value 2. So we can write that the limit of f of x as x approaches 0 is equal to 2. So those are two examples of how limits can exist even though the function doesn't exist at a certain value of x. So let's look at now some situations where the function does exist, or where the function is defined, in other words. I'll erase that too. Next we got, okay, this is a good one. Well, they're all good. This is just really good, just for you guys to see at this stage. So let's have this piecewise function, f of x is equal to 1 when x is not 2, and 0 when x is 2. So what we got going on then is a horizontal function, or horizontal line as our graph. There we go. So remember, don't overthink these. Make sure you know your algebra. This is just saying that the y value equals 1 as long as x is not 2. So it's 1 all the time except for one value of x. So we can draw a horizontal line like this. I'll just write y equals 2 just to make sure we're clear on what's going on. Now when x is 1 though, when x is 2, we're going to put a circle. So we have a circle or a hole at 2, 2. And we have a solid filled in point, so to speak, at 2, at 2 comma 0. See that? We got a hole here. We can also we also say that, or you may also hear it being called a jump discontinuity. Jump discontinuity. I like writing this word. I think it's cool, but it's not necessarily. Usually on the exam will be a hole or undefined. Well, sorry, not undefined. Okay, because in this case, the value of f of x, or the value of y, is defined when x equals 2. So in other words, let's write it down here. F of 2 is equal to 2. So the function is defined for x equals 2. But as you can see, the limit is not the same as this, because the limit of f of x as x approaches 2, oh my god, I wrote this wrong. Whew. Sorry guys, please forgive me, I'm usually better at this. The f of 2 is actually 0, is what I meant to write. I swear I know calculus really well, I'm nervous. I haven't made a YouTube video in a while. F of 2 is 0, so the function is defined there, and the limit of f of x as x approaches 2 is equal to 2. So this is an example where the function is defined and the limit is defined, and they're not the same thing. Right? Now, let's look at another one similar to that, or not similar to that, but like another case where you can have limits, but this one will be a good one actually, because it doesn't really do any of the things we just saw from these examples. So let's have f of x be equal to the absolute value of x over x. And this is actually good for you to know because they always have like one type of problem like this in the multiple choice section on your exam. So know that this is essentially just going to be equal to 1. If I put a 2 here, it would just be like 2. If I put a 3, 3. But this will be 1 on the positive side and -1 on the negative side. You can always plug and chug and verify, but it's always just helpful to kind of remember that. So we are going to have an open circle and a horizontal line to the right. We'll just write y equals 1. And we have a point here at 0, 1 that's not, that's not filled in. We have a hole at 0, 1. And down here at 0, -1, so we can write that this is the line y equals -1. We also got a hole. Got 2 holes here. Holes all over the place. Oh. So we got double hole action going on here. I hope that didn't come out wrong. Now, the function is not defined at 0. So we would write that f of 0 does not exist. It's not defined. 0 over 0, it causes a whole crap load of problems in math. 0, does that. But what about the limit? What would the limit of f of x be as x approaches 0? Now the thing is about it, you're noticing, on the right side it's going to this point, or this open circle. On the right side it seems to be going to 1. But on the left side it's going to -1. So they're not going to the same point. So when we're not going to the same point, that also means the limit does not exist. I guess technically you shouldn't write does not exist, but we can say it does not exist or it doesn't, or is undefined, or yeah. So again, they're not colliding or going to the same point from both sides. So we say that that's a situation when the limit does not exist. This is an example of where we can apply one-sided limits. I'll go over that later on, but I'll just show you what it is right here. Like we have a one-sided limit as x approaches 0 from the positive side, meaning that we're coming from here because that's where the positive numbers are. We put this little positive symbol right here to represent that, and this would then be equal to 1. And we have the limit as x approaches it from the negative side, or from the left. And let me see if I can fit it over here. Yes, I can. The limit of f of x as x approaches 0 from the negative side, little negative symbol here, is equal to -1. Yeah. So I'm giving you a sneak preview of that. But don't worry, there's a whole section devoted to this later on, towards the end of the chapter. But this is a good example of a one-sided limit function. Okay, so let's just do a couple more. 2 more. Demonstrating this. Demonstrating the other types of limits that you will probably see most commonly. So we're going to look at a function where it has an unbounded limit, or a limit or a function that just blows up. We say, I like to say blowing up because it kind of sounds like you're doing some serious science in that. Because we're going to have this guy, number 5. Let's have the function f of x is 1 over x squared. Yeah, 1 over x squared. All right, now Remember that's what these look like. It's going to be undefined at 0, but as we approach on the left side, we're going to be over here to the left of the y-axis. On the right side, it's going to look like this. So we don't ever cross the y-axis, we just blow up or get infinitely large from both sides. Y goes to positive infinity on both sides. Now, a lot of books won't write that in that way. They'll usually just say unbounded or does not exist. So I guess maybe don't get into the habit of this. But I like writing this. I would argue that's technically not wrong, but they can argue. A tough grader can argue that the way you write the sentence is technically incorrect. But what we would say is that the limit, what the heck? I'll get that in a second. The limit of f of x as x approaches 0 does not exist. It's unbounded. 0 can't be contained. Not 0, infinity can't be contained. Maybe 0 neither. Okay, one more, then I'll summarize this all. Thank you for sticking with me. For those who are still watching, I appreciate it. Feedback is always helpful. I'm willing to listen to criticism and improve. But here we go, number 6. We got this guy, and I'll show you later on when we do when I have the camera set up so that you can see how we can. I'm going to show you plenty of examples of how we can use the graphing calculator efficiently. But if you were to graph the function, the sine of 1 over x, you're going to see some craziness. We're going to see some oscillation behavior. Now, first, let's make sure we understand that the sine function can never get greater or less than positive or negative 1. So let's put a boundary line at y equals 1. And another boundary line at y equals negative 1. Like so. Now, your calculator will essentially be doing this sort of thing. Or actually, well, let me make it more precise. Like it's gonna do this, and then it's gonna just do this over and over and over, like there's no tomorrow. Yeah, and if you keep on zooming in, it's just gonna keep on doing that. We don't know what's going on there. It's maybe some sort of parallel universe or something. But the limit. Let's go with, is this blue? Can you see that? Yeah, you can. Nice. So we say the limit of f of x as x approaches 0 does not exist as well. This is an example of an oscillating function, oscillating behavior. F of x oscillates between negative 1 and 1. Oscillates. Woo. Hey. All right. So let's stop it there for the lesson. But I forgot what I was going to say. Now, again, we're going to go into many different cases, but know these ones. Make sure you practice the basic cases before we move on to the next section. I'm going to have a video over a lot of practice problems dealing with this. This is, again, just observing and plugging and chugging. And please, let me give me some feedback. Anything I can improve. I'm willing to work at it. And subscribe if you'd like this and are getting something out of it. And I'll see you guys in the next one. Bye.